We're all connected to each other biologically, to the earth chemically, to the rest of the universe atomically.
The sun has more perception and no.
And?
This is the sun, our closest star, and these are what? Solar flares. Solar flares. It's really hot. The Earth orbits the sun. When it faces the sun, it's daytime. When it doesn't face the sun, it's nighttime. This is the atmosphere. It's a way of getting it a warm Earth. Why do stars twinkle? When the star shines, when it hits the atmosphere, it wiggles. This is the moon. This is a crater. When the craters are made out of rocks that hit the moon. It orbits. It faces us one side and it orbits around the Earth. The moon has no light. It's just reflecting the sunlight, and it has no atmosphere. Stars are 1,000 what years?
I think nature's imagination is so much greater than man's. He's never gonna let us relax.
This is the first spacecraft to orbit a comet. So, Earth is here, the sun is here, Mars, and the comet, 603 comet, and deep space. So, this is the Rosetta spacecraft, this is the Philae, the lander. So, she's not here, and goes here, uses the sun and uses the sun's gravity, and goes here, and uses the Earth's gravity, then goes here, uses Mars' gravity, then goes here, orbits farther, and each time she uses the sun's gravity, then goes way out in deep space, then chases the comet for 10 years, then finds it, orbits it twice, then drops Philae. Philae lands in a canyon, and then we hope the comet goes over here so it gets more light from the sun, because Philae's in deep sleep and he needs light to hit his solar panel to wake up.
What did they find when they landed on the comet?
Organic matter.
Why is that important?
Comets could have brought life to Earth. So then Philae gets dropped by Rosetta. Then he bounces half a mile. Then lands on his side, bounces again, then lands in this canyon. Then he's in deep sleep. So
Standing on a planet. Really, I'm just a speck. Compared with a star, the planet is just another speck. To think about all of this, to think about the vast emptiness of space. Billions and billions of stars, billions and billions of specks. The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together.
This is a picture of an atom. There are three things that make up an atom: protons, neutrons, and electrons. Protons and neutrons in the middle of an atom make up a nucleus. A nucleus is in the middle of an atom. Electrons go around the nucleus, forming an atom. Atoms are very important because they make the stars, the planets, even us.
So this is the periodic table of elements. And I made a book about the fiery and fizzing metals. And I'm going to show you like the first three of them. Let's see. So the first one is hydrogen. It has one proton and one electron. And on the periodic table of elements, its letter is H right up here. Hydrogen. And it's a clear gas, so you can't really see it. And let's see. The next one is lithium. It has 3 electrons and 3 protons instead of 1. And this time it's Li. It's the second one. And lithium is the lightest metal of all the metals. And I think it's used to make like rockets and planes. And then the third one is sodium, and it has 11 electrons, 11 and 11 protons, and it's Na instead of Li. And we eat sodium, and it helps send nerve signals. Like, I think it's like when you fall, it helps send nerve signals. And then I think the last one is, the last one is potassium. Well, not the last one, but the other one is potassium. And it has 19 protons and electrons, and on the periodic table it's K instead of Li or H or Na. And it's in bananas, and it's in bananas, and it has 11 or 19 of each. And then I think this might be the last one I'm going to show. But the last one is rubidium. It has 37 of each, and it's Rb. And it's like in TVs and like, I think like cars and GPSs. And then it's, Rb and 37 of each. And then there's cesium, which has 55 of each, and it's Cs, and it's in and it has the largest amount of, I think, protons and electrons. And then there's francium. Mercury Atlas was the first rocket to carry an astronaut into orbit. It was as powerful as 747 jumbo jets. Rockets tear up a lot of the ground when they launch. There's big water tanks around the rocket, so when the rocket fires it down, they let go of the water or something, and so it keeps it from destroying too much.
What kind of fuel do they use?
The fuel that they use is hydrogen and oxygen. So it tears up a lot of the ground.
We live in an in-between universe where things change alright, but according to patterns, rules, or as we call them, laws of nature.
Astronomy is the study of celestial bodies or objects in space such as planets and our sun. This is in and out. Purpose to demonstrate forces that keep satellites in orbits. Result, the spoon in a circular path with only the weight of the tape pulling on the attached string. Purpose to demonstrate how Saturn can be seen through its rings. Results. Two black rings is seen, but you can see through the spinning blades. Galileo was born on February 15th, 1564. He believed something other people did not. He believed that the Earth and the other planets orbited the sun. Most other people believed that the sun and other planets orbited the Earth. Galileo died in the year 1642. We are going to do an experiment that we got from a book about him, his biography. In this experiment, you test the law of gravity. First, you hold an orange in one hand and a dime in the other. Drop them both at the same time. Even though the orange weighs more, they hit the floor at the same time. This is because gravity has the same effect on them both. Now do this over again, this time with the paper and the orange. The paper will fall to the ground quite a bit after the orange. This is because the paper can catch on the gas of Earth's atmosphere, and that slows it down. Now crumple up the paper and do the same thing. The same thing would happen on a planet with no atmosphere. The paper and the orange fall at the same time.
Across the sea of space, the stars are others. We've traveled this way before, and there is much to be learned.
3, 2, 1, go.
Here's our solar system. Sun. Temperature.
Temperature 27 million degrees Fahrenheit. Gravity 27.936. Size 1 trillion miles. Day 27 days. Year no year. Moon 8 plus many more.
Mercury, the closest planet to our star.
Size 3,3032 miles. Day 58.6 days. Year 88 days. Temperature 806 to minus 274. Gravity 0.37. Moon 0.
Venus, the second closest star, the second closest planet.
Year 224.7 days. Day 243 days. Gravity 0.905. Size 7,500 miles. Moon 0. Temperature 878 degrees Fahrenheit.
Here's the Earth.
Gravity 1 times itself. Temperature 143 to minus 122. Size 7,957. Day 24 hours. Year 365 days. Moon 1.
Mars, the red
moon.
planet. No, I mean the moon.
Moon 0. Temperature 28 to minus 300. Year 27.3. Day no. Gravity 0.166. Size 2,156.
I kind of said this earlier, but here's Mars.
Size 4,220 miles. Temperature 32 to minus 166. Gravity 0.37 times Earth. Day 24.6 hours. Moon 2. Name after the Roman god of the war.
Here's Jupiter.
Size 88.846 miles. Year 4,331 days. Day 9.9 hours. Temperature minus 256 to minus 166 Fahrenheit. Gravity 2.31. Moon 63.
Here's the Saturn.
Size 74,898 miles. Temperature minus 292. Gravity 0.9. Day 10.7 hours. Moons 62. Year 10,747 days.
Here's Uranus.
Gravity 0.903. Moon 27. Day 17.193 hours. Year 84.01 years. Size 15.759 miles. Temperature minus 243 Fahrenheit.
Here's Neptune.
Size 30,775 miles. Temperature minus 346. Gravity 1.1. Moon 13. Year 59,800 days. Day 16.1 hour.
Now here's Pluto, the planet, technically a good planet.
Size 1,485 miles. Temperature minus minus 382 Fahrenheit. Year, 90,588 days. Day, 6.4 days. Gravity, 0.06. Moon, 3.
Earth, the planet. A little bit of a dwarf planet.
Size, 1,550 miles. Year, 205,000 days. Day, unknown. Gravity, 0.08. Temperature, minus 382 Fahrenheit. Moon, 1.
I know that the molecules in my body are traceable to phenomenon in the cosmos. That makes me want to grab people in the street and say, have you heard this?
I bet is are made of 65% and oxygen and 18% and carbon and 10% and hydrogen and type of lots of other elements. And stars are a lot like this, and they're made of hydrogen and 71% and 27% and helium and then 2% of all the other elements. So we're really made out of star stuff.
Like the extinction of the dinosaurs is thought to have been caused by an event when something hit the planet, like a giant asteroid. So if we zoom out, so this is the main asteroid belt, the ones that are kind of yellow, or not yellow, the ones that are kind of purple and pink and white. These are the main asteroids. The color denotes their composition. So you notice that as you move away from the sun, they're changing composition. The white ones mean that the asteroids are made more out of metal than they are rock. And then the sort of pinky purple ones mean that they're made more out of rock than metal. That's because it has to do with the temperature of them. When you're close to the sun, it's easier for metal to condense than it is when you're far away from the sun. Or when you're far away from the sun, actually, it's easier for rock to condense than when you're closer to the sun. So depending on your distance to the sun, stuff is made out of different materials. Now these guys here are called the Trojans. The solar system, it has more mass. So you weigh up all the planets. The sun weighs more than all the other planets put together. The sun has 99.99 times percent of the mass of the solar system. So the sun is the biggest thing, but Jupiter is the biggest planet. Jupiter has these moons that are orbiting it. You guys see these little moons?
Galilean.
Yeah, exactly. Good job. These are the Galilean moons. So what are their names?
Low.
Europa,
Europa, yeah.
Io,
Astro.
Callisto. Yeah, I'll go through them. So you guys know most of them, or at least I can see you've learned them. So the first one, the one that's closest to Jupiter, is called Io or Io, depending on what country you live in. British people tend to say Io, Americans tend to say Io. Our moon, as far as moons go, is not, I mean, it's really awesome because it orbits us and it's close by and it's the only place in the solar system that we've ever put a human on besides the Earth. But compared to some of the other moons, like the Galilean moons and Titan, which you guys mentioned, it's not as interesting as some of those other moons in terms of its characteristics. But here's the back side of the moon. So we usually only see the side of the moon that faces us. We don't usually see the back side of the moon. So this is what the back side looks like. And you notice how it doesn't have these large basins on it.
Yeah, that's the Earth.
Yep, so there's the Earth. So we're centered on the moon right now. So if I were to zoom out and turn on the orbits, you'll kind of get a better sense of the perspective that we had before. So we're sort of following the moon right now. And so it looks like the Earth is moving around the moon. Alright, so here's our little moon, our friendly little moon. These Maria, just a quick note, these are giant impact basins that happened on the moon. So a giant impactor hit the moon and melted the surface. And that's what created those Maria. People used to think they were seas before we actually knew what they were made of.
Is Mario a video game?
Alright, so who can guess what planet we're checking out next?
Saturn.
Yes! Saturn's my favorite planet because it is so pretty.
Pluto's one. You know, if you stand on its rings, would you fall right through them?
So the rings are really interesting. So these rings are made out of pretty much mostly all water ice. The water ice is really shiny and reflective. So if you think of freshly fallen snow and how shiny that is, it's really shiny stuff. And since Saturn's rings are mostly made out of water ice, they have that same shiny reflectivity. Jupiter, Uranus, and Neptune all have rings of their own, but they're really, really dark rings, and they're hard for us to see. Saturn is the lucky one, and they've got really super bright rings. Now, if you were to stand on these rings are made up of a whole bunch of particles that are orbiting around Saturn. Some of them are small particles the size of dust grains, and some of them are really big particles the size of cars, or maybe even buildings for the biggest ones above. Yeah.
Is Saturn actually spinning or is it the ring?
Saturn is spinning, and its rings are also spinning, although you can't see it.
I was responsible for the fire protection in the vehicle assembly building, which was, at the time, it was the biggest building in the world. That's where they put the Saturn moon rockets together.
I
It's in
actually
your room.
have a question about fire control. How come the metal on the rocket doesn't burn up when it re-enters the atmosphere? Because like meteorites do, and usually do when they're made of metal.
You know, there's two answers to that, because there's two different ways. When the Apollos and the Geminis and the Mercuries came back, they had a material on the end that faced the atmosphere, it faced the air. That got really, really hot, and parts of it kind of melted off, and that took the heat away. Okay?
That's
Now,
cool.
on the space shuttle, they do it a different way. They've got some special tiles that are made out of silicone, and they're just a really, really good insulator. They don't have to melt away. As a matter of fact, they don't melt away. They just get really, really hot. They get up to about 3,000 degrees Fahrenheit, but that it just stays on the surface of the tiles. It never gets through to the metal of the spaceship itself, the orbiter.
That's cool.
Engines provide more thrust than the weight of the vehicle. Okay, the Saturn V, the moon rocket, for instance, the vehicle weighed 6,300,000 pounds.
Whoa.
But the first stage engines produced 7,600,000 pounds of thrust. So that made it go really, really fast. Okay, and the second stage, by that time, most of the weight is gone, and the second stage is still producing a lot more thrust, and it just keeps going faster and faster and faster until it gets to 17,500 miles an hour. And then at that point, it's just falling around the Earth. That's all it is. An orbit of the Earth, a satellite or anything else, a space shuttle, it's constantly falling, but it's falling in a circle because it's going this way so fast. Well, gravity's making it go this way. So they just keep falling in a circle. But for instance, most satellites and most spaceships still have some left. On the shuttle, have you guys seen a shuttle with that big orange fuel tank?
Yeah.
Okay, that only powers the three of the engines on the back of the orbiter. Okay, when that's gone, those engines don't work anymore. But on top of those, there's two smaller engines, and they have fuel inside the spacecraft. And most satellites, they don't have as much because their engines are a little smaller. But for just being able to go back and forth, you know, if they're going like this and they want to go like this, they have to change orbits with a rocket, and they have some fuel on board. Okay, but once they get up there, as long as they keep falling in a circle, they don't need any more. Okay. Hydrogen has a really high energy density.
We got it. We can do it.
Okay. Okay, and it's for weight, it'll produce more energy than almost any other propellant you can have. But you have to have something to burn it. which is oxygen. So you have a tank of liquid hydrogen and a tank of liquid oxygen. You put them together and you ignite them, and they burn, and what they make is water. When you combine hydrogen with oxygen, you end up with water. But you also get a lot of thrust, a lot of power that'll lift the rocket off the launch pad.
The spaceship always land in the water.
Well, America's the United States has always chosen to do that before the space shuttle happened. The space shuttle actually lands like a glider. It lands on a landing strip. The Russians, when they do their space program, they land on land. We just felt it was safer to do it in the water because it wouldn't, when the spacecraft hits, if it's going too fast and it hits ground, it could smash up. If it hits water, it'll go right into the water and then bob back to the surface. Hopefully not hurting anybody.
But the water is strong but the water is super strong if it's hitting like super fast.
If it's going super fast, yeah. But by the time it hits, it probably shouldn't be going any more than a few hundred miles an hour. And that's bad, that's not good. But the spacecraft can stand that. The only time
So this is a scientist who is looking through a microscope specialized to see atoms.
Okay.
So this is really magnified.
Sweet.
Like
Billions of times. So, are there the correct number of electrons going around that side? Can I see those 6 ones? Because I thought that was pretty cool, I think. Oh, 2. Nice.
And then each 2 represents 1.
Each what? What are those?
represent 1 proton or neutron.
In the...
In the nucleus, since they're a little bigger electrons.
Right. Are they balanced out? Sweet. What if they were unbalanced?
The nucleus might go apart.
Oh. What does a carbon atom split into? Do you guys know? No? That's okay.
As you can see up there. And this is charcoal. Charcoal has carbon in it. This is the human and the life represents. The human in the tree represents life.
This is graphite.
Life has at least a little bit of.
Oopsies, I pulled up the wrong page.
There, I'm almost ready.
You want to tell me what the things are, Benny?
I'm ready,
Wait, I pulled up the wrong
but
page.
not ready. So this is 6-7P Comet.
Okay.
And then this is Rosetta, and then in here is Billy.
Okay. Okay, I'm going to film
And
it.
then this is Philly.
Sorry.
This is a picture of Billy, and this is the information. That's the comet's information. Big picture.
And this is Dylan
Whoa.
playing a video.
Hi.
Go.
Okay, wait, let me get there. Here, I'm going to be right here next to you. Sorry. Whoa.
It's not. Yes, it is. That's meant to just go for.
Uh-huh. Oh, super.
But
Whoa.
no. And that probably not.
No, it's not meant to do. But that's what it's meant to do, just for
Uh-huh.
just.
Super cool. Okay, I'm going to stop the video.
See you next time.
Okay, so it starts as the half moon, crescent moon, and then full moon. And then if you look in the internal diagram, which is right there, you should be able to see. So if you look through this hole, you will be able to see the light side of the moon, and this hole, the dark side. And so you should be able to see the moon on top of the Earth, which was basically the only thing we could do. And then the Earth below it, and you will see the crown here with 11 crank that to see the moon and the Earth. And when you look through there, the sunlight is where you're looking for the moon. So the sun is
Not 2 seconds though, it's 2 power. So that's how you slow down the motor. If you make a bigger number, it's going to make the motor go faster.
Can I see?
But now what do you want to do after you set the motor power? After you tell it how fast you want it to go?
think, Hazel?
I need to use the weight.
So you're gonna start the motor. And then what are you gonna do? Why'd you get rid of your stop?
Yeah, why'd you get rid of your stop? Now I'm going to make this program longer.
You're gonna stop and then you're gonna what? What are you doing after you stop? Because you want it to stop for a little while, right?
Well, I just wanted to make this on. I just want to make like this program like a pretty, like say a little longer. Because this is like a combination program to me.
So tell me what it's gonna do though.
Well, so practically start, go that way, go left, wait, start the same thing, and wait, like it's going to do like the same thing a couple times.
Is it ever gonna stop?
I'm going to stop button somewhere. I'm going to make this go to the other side.
Here, hey, Jackson, stick that back where it was. If you just click on that arrow, just click on it once.
Oh, look at that. Nice.
8 to 2. Start turning the motor left. Wait for a few seconds. Set the speed to 2. Start turning the motor right. Wait, did we ever stop the motor?
No.
So it started turning left, and then after 5 seconds, it started turning right, and then it's going to start turning left again, and then it's going to stop.
Oh, so what do we need?
So it seems like it's, if it was Edbot, I think I'd be doing this.
So what do we need? So what do we need?
I just did it.
No, you have to move because
Oh yeah, I would be repeating forever until someone finally pushed stop.
So what do we need, Hazel?
That's cool. Nice.
we might need it to wait for a little
Nice.
longer.
I like your.
Or does it need to completely stop?
Shining my head. Just shining my head.
Who did
Why
that?
don't you try that?
Yep. Hey, Jackson, Hazel's gonna take a shot at it, okay? So it stops. Now what do you want to do after it stops?
It needs to repeat again.
Okay, so you're gonna tell it to stop, and then it's gonna go right back to start.
And
So
what-
if
yeah.
you want it to wait, if you want it to stop for a little while, what do you want to put at the end there?
Oh wait.
Can you give that a shot?
Perfect. Can you write Rosetta on that? No, we're not gonna start gluing the ideas on.
It's a little easier if you use both hands. So use one hand to hold the button while you're dragging it up.
Can you come actually here for a second?
And then, yep. And then if you let go of the button, it'll drop it there. Now what do you think that's gonna do?
Wait for 10 seconds and then repeat.
Should we give it a try? Jackson, okay, we're gonna give it a try.
Ah, thank you.
Hey, Jackson! That's not gonna work.
So Jackson, we're really trying to get some work done here.
This is the electrons. The nucleus is the yellow photons. Us are the electrons. And it looks like a green.
The sheet needs to look at it.
The next one is.
Oh!
All right, who's in this team?
Okay. Guys.
Who's a protron? Oh, look at those protons wiggling. Who's a neutron? Who's a neutron?
Almost
standing on a planet. Really, I'm just a speck, I'm just a speck. Compared with a star, the planet is just another speck. To think about all of this, to think about the vast emptiness of space. Billions and billions of stars, billions and billions of specks. The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. The cosmos is also within us. We're made of star stuff. We are away. The cosmos